move on to discuss a very important concept which is used in many applications of probability, which is referred to as Bayes rule. But before we discuss about Bayes rule, we introduced what we refer to as a law of total probability. Now, let E and F be any events. In other words, if I have I have a sample space. Suppose I have an event F which is given here. Suppose this is my event F, then this shaded region is my F complement. In other words, that I can mutually exclusive events. So, F and F complement are always disjoint and mutually exclusive. So, let us shade this event. So, let me use a different color to shade this F and F complement. So, I am just looking at F. So, I have this event F. So, let me use a lighter color. So, I have F here, F is the white color here, and let me use a lighter color, say this, let me use a lighter color here, blue, and that blue is going to be my F complement. Okay. This light color blue is my F complement set. Now, let us look at an event E, another event E that is happening, but the way this event E is happening is I am having information of this event F that has occurred. This, when I talk of this event F, I know that they are mutually exclusive in the sense that F can occur or F complement can occur. Now, let me look at an event E that is happening. So, when I talk about an event E that is happening here, this event E is happening here. So, you can see the event E that is happening. Now, if you look at event E, now you can look at this event E has an intersection with F, which is given by this green portion, and the intersection of this event E with F complement is this pink portion. That is what we are trying to say. So, I have a mutually exclusive F and F complement. When I look at event E has an intersection with F, which is referred to as this area, which is E intersection F, and this portion is the intersection of E with F complement. So, I can actually write any event E as E intersection F union E intersection F complement. So, what does the law of total probability say is, when I have mutually exclusive F and F complement from my sample space, then I can express my probability of E as probability of E intersection F plus probability of E intersection F complement. This is from the addition rule. Now, from the multiplication rule, I can state this as probability of E conditioned on F into probability of F plus probability of E conditioned on F complement into probability of F complement. Recall, probability of F complement is 1 minus probability of F. In other words, the way we can articulate it is, the chance of this E happening is a weighted average of E happening given F has happened, and the chance of E happening given F has not happened multiplied by the respective probability of F happening and F not happening, and this is what is referred to as the law of total probability, which says that in order for an outcome to be in E, it should be either in E and F, which is this green region, or it should be in E and not in F, and I can tell that this is what we have got. Now, this expression probability of E equal to probability of F into probability of E given F plus probability of F complement into probability of E given F complement is what is referred to as the law of total probability, where each conditional probability, I have two conditional probabilities, it is weighted by the probability of the event on which it is conditioned. That is, probability of E given F is conditioned on probability of F happening, probability of E conditioned on F complement is conditioned on probability of F not happening. Now, we can actually extend this to many events. For example, again let us go back to my sample space. I can partition my sample space into events F1, F2, F3 and Fk, okay, such that they are mutually exclusive. So, you can see F1, F2, F3, Fk are disjoint, and they are exhaustive in the sense F1 union F2 union F3 union Fk should be my sample space. That is what I mean by exhaustive. Then for any event E, so let me draw an event E here, let this be my event E, and let me color it using a lighter color. So, this event E, so this green area is now E intersection F1. Similarly, the orange area is E intersection F2. I have the purple area is the E intersection F3. Similarly, I have this area, the yellow area is E intersection Fk. Yellow is not very visible, so let me make it red. So, this is E intersection Fk. I can write my event E as the union of these disjoint sets, and now I can apply my addition rule, which says probability of E is probability of E intersection F1 plus probability of E intersection F2 plus probability of E intersection F3 plus probability of E intersection Fk. Applying my multiplication rule, I get this is equal to probability E conditioned on F1 into probability of F1 plus probability E conditioned on F2 into probability of F2 plus probability E conditioned on F3 into probability of F3 plus probability of E conditioned on Fk into probability of Fk. So, we can see that each of these conditional probabilities of E happening weighted on the probability of the event it is conditioned on. Here again I have E given F2 into the weight of the probability of the event it is conditioned on, which is F2, and this is what is referred to as the law of total probability, which I can rewrite as the following. I can rewrite this as summation I going from 1 to k probability E conditioned on F5 into probability of F5. So, this is what is referred to as the rule of total probability or law of total probability, which states that suppose we have F1, F2, Fk which are mutually exclusive and exhaustive, then for any event E, the probability of E happening is expressed as the weighted average of the conditional probabilities of E happening conditioned on these events. So, now let us look at an application of the law of total probability. So, now the application, an insurance company believes that people can be divided into two classes, those who are prone to have accidents and those who are not prone to have accidents. So, if my sample space is the entire population of people, the insurance company believes that I can divide this entire space into two classes. One class, let me call it F, is the accident prone and the other one is the non-accident prone. And we know that these two are distant. So, I cannot have a person who is both accident prone and non-accident prone. Now, the data indicate that the accident prone person will have an accident in a 1 year period with probability 0.1. So, I have another event that is being defined and let me call that event to be E, which is the event is a person or a policy holder meeting with an accident in a 1 year period or within a year. Now, what does this indicate? An accident prone person will have an accident with probability 0.1, whereas the probability for all others is 0.05. So, what do we understand by this? The chance of a person having an accident within a year given he belongs to the accident prone class. That is what this means, that an accident prone person will have an accident within a 1 year period and this probability is given to be 0.1. Whereas, the policy holder would meet with an accident. So, the policy holder who is meeting with an accident also will belong to these two classes. So, now my event E, which is the chance that a person meets with an accident within a year, could happen in two ways. The person is meeting with an accident within a year and is accident prone, or the person is meeting with an accident within a year, but is a person who comes from the non-accident prone class. So, these are the probabilities that are given to us. Is this conditional probability is 0.1 and this conditional probability is 0.5. Suppose that the probability is 0.2 that a new policy holder is accident prone. So, we have defined F to be the probability of a person to be accident prone, and that probability we have is 0.2, hence probability of F complement is going to be 0.8. So, the question that is being asked is, what is the probability that a new policy holder will have an accident in the first year? So, that is what is probability of E, that is what is being asked. So, let us look at the solution. So, I have the following which is given to us. So, let us look at the solution. So, let us look at the solution in a more structured way. So, I have the following. So, let us look at the solution. So, again we have defined as before, E is the event that a new policy holder will have an accident in the first year, and F is the a new policy holder is accident prone. So, these are the probabilities given to us as before. Probability E given F is 0.1, whereas probability E given F complement is 0.05 and probability of F is 0.2. So, my law of total probability tells that probability of E is equal to probability of E given F into probability of F plus probability of E given F complement into probability of F complement, which is equal to 0.1 into 0.2 plus 0.05 into 1 minus 0.2, which is 0.8. So, I get a 0.02 plus a 0.04, which is equal to 0.06. So, that is the answer which we have, which is equal to 0.06. In other words, we can state that there is a 6% chance that a new policy holder will have an accident in the first year. There is a 6% chance. So, now we come to state what is very important and what is very popularly referred to as a base rule. Recall what we had in the law of total probability is, suppose I have two disjoint events f complement and I have an event E here. I can write E as E intersection F union E intersection F complement to give the law of total probability is which E given F into probability of F plus probability of E conditioned on F complement into probability of F complement. Now, suppose some additional information is given to us. For example, here going back to this example, I am interested in knowing what is the chance that a new policy holder will have an accident in the first year. Now, I go back and I see that a policy holder has had an accident in the first year. Now, this is the new information we have. Now, I might be interested in knowing that given this information that a policy holder has had an accident in the first year, did he come originally from the accident prone class or the non-accident prone class? In other words, given E, I am interested in knowing what is the chance he came from an accident prone class. Hence, probability of F given E is given by this expression, and this expression is what is popularly referred to as the base rule. F conditioned on E is probability of E conditioned on F by the probability of E, which is probability of F into probability of E conditioned on F into probability of F complement into probability of E conditioned on F complement. Now, I can extend this base rule, I can extend this to my F1, F2, just as I extended it to my law of total probability to have k events, and I have this event E. Now, for any event f k conditioned on E, I know is equal to probability of f k intersection E divided by probability of E. This is probability of E conditioned on f k into probability of f k, that is my numerator, whereas my denominator I saw was probability of E I going from 1 to k, probability of E conditioned on f I into probability of f I. Now, this is what is popularly referred to as my base theorem, which states the following, that suppose I have f1, f2, fk which are mutually exclusive and exhaustive, then given any event E, I can write probability of Fi conditioned on E is probability of E given Fi into probability of Fi to summation I going from 1 to k E conditioned on Fi divided by probability of Fi. So, this is what we refer to very popularly as the base rule. Now, let us go back to our insurance policy problem and apply the result there. So, we know that again I have two classes, accident prone and non-accident prone. We were interested in knowing what is the chance of a person E, where E is the event of a person having an accident within a year. So, we found out probability of E was equal to 0.06. Now, the question is, if a new policy holder has had an accident within the first year. So, I am conditioning the problem on E. The accident has happened within the first year. What is the chance that the person was accident prone? So, applying Bayes theorem, I know this is going to be E given F into probability of F divided by probability of E. We already computed probability of E in our earlier problem, which was 0.06. Probability of E given F I know is 0.1, probability of F is 0.2. So, I have this is 0.02 by 0.06, which is 1/3. In other words, if a new policy holder has had an accident in the first year, the chance that he or she is accident prone is 0.33. You see that independently this chance that a person was accident prone was just 0.1, but given the information that a new policy holder has had an accident, you can see, so you can notice that the chance of a policy holder being accident prone was 0.2, but given the extra information that a person has had an accident within a 1 year period, you see changes the probability of being accident prone to 0.33 or increases this probability. So, within the subset of people who have had a accident within a year, you can see that the chance of a new policy holder being accident prone is increased from 0.2 to 0.33. So, this is the solution, and I have the probability of F given E is 1/3. Hence, given that the new policy holder is has had an accident in the first year, the conditional probability is prone to accident is 1/3. So, that is what we have. The conditional probability is equal to 1/3. The unconditional probability was 0.2. So, what we have learnt in this section was, first we learnt what was the law of total probability, which was probability of E is probability of E given F into probability of F plus probability of E given F complement into probability of F complement. In other words, the probability of any event happening is the weighted average of that event conditioned on the occurrence of an event and the non-occurrence of an event. These two, the mutual exclusivity of these two events is very important. Not only the mutual exclusivity, the exhaustiveness. So, when I have more than two events, I said that these two are mutually exclusive and they are exhaustive. So, F1 Fi intersection Fj equal to null set. This is the law of total probability, and the Bayes rule states that given this information, then probability of E given F into probability of F divided by probability of E. I can substitute this here to get the Bayes rule. A word of caution. So, here we have two important things which we have learnt. One is what are mutually exclusive or disjoint events, and the other is what are independent events. These two should not be confused, they are not the same. Mutually exclusive events is the occurrence of an event prohibits the occurrence of the other. For example, when I am tossing a coin, occurrence of a head does not allow a tail to be an outcome. That is when I call them to be mutually exclusive, whereas independent event says that the unconditional probability of an event happening is the same as the conditional probability of an event happening conditioned on the occurrence or non-occurrence of another event. So, with this we come to the end of the introduction module of probability, where we first started with the building blocks of probability. we introduced through the concept of a sample space. Once we introduced the concept of a sample space, we spoke of what was an event. Even before the concept of a sample space, we discussed what was a random experiment. So, whenever we are talking about a probabilistic scenario, we first identify what is the experiment, the sample space and the events. Then we introduce the axioms of probability, namely probability of any event would lie between 0 and 1, probability of the sample space is 1 and the probability of countable union of disjoint sets is probability of the sum of the probabilities. EI intersection EJ is phi for all ij. Once we introduced this, we went on to talk about probability of the complement. Then we had the general addition rule, which said probability of E1 union E2 equal to probability of E1 plus probability of E2 minus probability of E1 intersection E2. This is what we refer to as the addition rule of probability. Then we introduce the notion of conditional probability. Where we spoke about the probability of E conditioned on F to be probability of E intersection F by probability of F, provided probability of F is defined. Then we spent time in understanding what was a multiplication rule, which is just another way of restating my conditional probability definition. Then we introduced the notion of independence of events. We restated the multiplication rule for independent events to be the product of the probabilities. And finally, we looked at what was the Bayes rule or the Bayes theorem. Here we introduce the law of total probability and the Bayes rule. So, this is a summary of what we have done so far. Now, the next topic which we are going to discuss is the following. When we go to the next, now given this knowledge, we are going to go and understand what we mean by random variables. So, the next topic is to understand what we mean by random variables. When we talk about random variables, we will be introducing the notion of a distribution of a random variable, expectation of a random variable, standard deviation, the variance of a random variable and other concepts. In particular, we will be focusing on two very well known distributions, namely the binomial distribution and the normal distribution.